everyone. Today we're going to learn about fracture. Now, fracture is the separation of a structure into two or more pieces. Fracture mechanics is a study of how cracks initiate, propagate, and ultimately lead to fracture of structures. A key concept, or probably the most important thing about fracture, is that it necessitates the presence of an initial flaw. So there has to be some initial defect in our structure from which fracture occurs. Now, cracks exist in parts even before they're put into service. These cracks could be due to flaws, inclusions, defects. It could be something as simple as machining tool marks from trying to machine our part. It could even be a defect from simply a mishandling of a component. Some examples we can see in the real world or like in metal 3D printed components, where when they come out of the printer, they can have really rough surface defects. Or in terms of laser-based metal 3D printing, you can have internal porosity and defects within your structure as your initial flaws. One of the manufacturing areas where we see the most flaws is in casting. Casting is a process that has many different types or categories of defects that can be present within our components. And then if we do have a part and we machine it or try to polish it, we're still left with machining tool marks of different levels of surface roughness based on the method used to machine a part. So an initial flaw or a defect isn't just something that we can maybe see with our naked eye on a macro scale, but it can be very small defects in the surface that cracks initiate from. Now, initial flaws, they always exist and they range from the nanoscale, from very, very small scale to the macro scale, what we can see with our eyes. Now, from these flaws, cracks can grow during service. So if, say, we have loads that are cycling, then a crack can grow from an initial size and get longer and longer. Now, since flaws always exist in structures, in every structure there's some flaw, it could be the nanoscale or even the atomistic scale, there's a need for us to develop a damage-tolerant design philosophy, a way that we can manage the presence of flaws and defects in our structures and be able to continue to fly our airplanes or drive our cars. So in damage-tolerant design, a few things are done. First, we establish a safety factor, a factor at which we will remove our part from service before it actually fails. The next thing we do is we need to assume the presence of a flaw of some initial size within our structure, some detectable size. Then we need to detect the initiation of that flaw and monitor its growth. And if it grows up to our safety factor limit, we then need to remove those parts from service and retire our component or repair our part so that it can have rejuvenated life, right? So what happens when we fail? What happens when we make a mistake in design? Well, here we have a case study for the United Airlines Flight 328, which exhibited an engine failure during flight. Now, this case study occurred on February the 20th. It was a Boeing 777, and the engine that had the failure was a Pratt & Whitney PW 4077 turbofan. Now, what happened in this flight? Well, the primary cause of failure was a fatigue crack in a single fan blade, so that's a compressor blade within this engine. The crack initiated on the interior surface of a cavity within the hollow fan blade. It wasn't detected during service, which the investigative bureau determined was inadequate and infrequent. So this is what happened during the flight. The fan blade, shortly after takeoff, separated. It fractured at its root. The blade, the separated blade and other debris impacted the engine fan casing, and was contained by the casing of the engine. But the nacelle failed. The engine's housing failed and tore apart, and then the engine caught fire. Right, and so the flight crew declared an emergency and were able to successfully land. Luckily, no one was injured during this flight, but a falling debris did damage some property on the ground. So this is a case where uh, in damage tolerant design, if we do not maintain proper inspection intervals and inspect any component that might exhibit growth or crack initiation or growth of a crack, then we can have these catastrophic types of failures, these very, very dangerous failures. So below here are a couple of images. Here is the engine in the study. We can see this is the fan blade that sheared off and failed and impacts the housing. This is the actual residual blade left itself. We can see the blade is hollow. And from the inside, we can see ratcheting marks. This is an indication where the crack initiated, and it propagated up to a certain length, and then fracture, complete separation of this blade occurred, right? Now, there's more information you can learn about this particular case study. You can hit the wiki, and then there's also a supplemental video in the Machine Element Supplemental. But let's get back to the heart of this, fracture mechanics. Now, thus far, we've learned about the effect of stress concentrations, where if we have a geometric discontinuity, like that inner channel of this blade, that change in shape can lead to a massive increase in the state of stress in the vicinity of that geometric concentrator, right? And the problem, however, with stress concentration factors is that when we have very sharp defects or cracks in our structure, the stress concentration factor charts breaks down. It starts to approach infinity. It's these equations say that the stress intensity, stress is equal to infinity in the case of very sharp cracks. And so we need to move to a different method in order to manage the presence of the initial flaw. And that method is linear elastic fracture mechanics, LEFM. This is used to predict fracture in structures with sharp defects and analyze crack growth in materials, how cracks can grow in a controlled rate until they get to a critical length where fracture occurs. Now, in LEFM, this is for brittle materials. So this is assuming fracture is occurring without yielding or very, very limited yielding within a structure. So with that said, we've got the basis of fracture. In our next video, we'll learn how to calculate LEFM parameters.